Amides. They're almost the same as the anions that I've shown you here. All I'm going to do here is I'm going to take the aspartate carboxyl and make an amide out of it. And so if that was called aspartate, we're going to call this asparagine. Okay? And we can't use the A because that's alanine. We can't use the S because that's serine. So we use the N, asparagine. And you can see I can obviously do exactly the same thing with glutamate and make an amide out of that. And if I call the amide of aspartate asparagine, what do you think I'm going to call the amide of glutamate? Glutamine. Well, now again I'm in trouble because I can't use the G because that's, and I can't use the L because that's, and I can't use the N because that's, so I'm going to use Q. I don't know why Q. I didn't make this stuff up. Okay. Now there is something interesting about these amides. Both amides are polar. Okay. Now of course I should have pointed out the anions have what charge? Yeah, they have a negative charge. And just as you might have expected, if I have anions, I must have cations. There are 3 of them here. What's the charge on a cation? Positive. Here's an easy way to remember it. When I wanted to be a biochemist since I was a little kid. When I was in high school, I took a college, my high school had a college-level biochemistry course. We actually used Leninger and Stryer. And I had a teacher, Miss Mazer. And Miss Mazer loved cats. And so for her, cats had a positive affinity. So she taught us that cats were positive. Cations were positive. That's an easy, quick way you can always remember from hereafter that cations are positively charged. Okay, let's draw some of those side chains. So the first one that we're going to draw is this. CH2, 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 NHC. Now, I'd like you to notice this is the side chain. And this is called arginine, ARG, arginine. Single letter code R. And this has a special group in it. This has a guanidino group. And this guanidino group has a very unique property about it. Okay? If I simply draw the guanidino group, I can draw this guanidino group in several different ways. Or I could draw it like this. Three different resonance forms, where all I've done is change where the carbon-nitrogen double bond is, from this nitrogen to this nitrogen to this nitrogen. And as a result, it's remarkably stable because I have 3 resonance forms that I can protonate. It's very easy to protonate. And so its pKa turns out to be on the order of about 12.5. Easy to protonate, right? Because look, I can distribute that positive charge among the 3 different nitrogens in the guanidino group. Two others to talk about. CH2, beta, gamma, delta, epsilon, NH3 plus. Okay? This side chain is simply a linear chain of 5 carbons that ends in an amino group. Okay? If this is my alpha carbon, this is my beta carbon, gamma, delta, epsilon, and this is my epsilon amino group. This amino acid is called lysine. Okay. Now I'm in trouble again, right? I can't use the L because L is, and I can't use the Y because the Y is, and I can't use the S because the S is, so I'm going to give it the letter K. Again, I don't know why. I didn't make it up. Last one. Side chain looks like this. This is histidine, goes by single letter code H, and it has an imidazole ring as the main component of its side chain, linked by this methylene bridge. Now, I can draw this in the protonated form in two different ways. I can draw the protonated imidazole like this. It's still aromatic. It doesn't lose aromaticity. But I can draw this in a resonance form like this. I have two forms in which I can draw this in the protonated state by distributing where I put that positive charge, either on this nitrogen or on this nitrogen. And as a result, it's pretty easy to protonate. When I do the titration, what I find is this has a pKa of about 6.1. And that means that at physiological pH 7.4, right, most of it will be unprotonated because the pH is above the pKa, but some of it may be protonated. And in fact, if I change the local environment to change the pH, I can convert this from its acid form to its base form. And we will see an example of that shortly. And if I go through and show you the data, this is the titration curve. This low pKa group, what am I protonating here? What am I protonating here? The carboxyl group. And up around 9.5, what am I protonating? The amino group. And here it's 6. That's that imidazole ring. Okay. Now, to make life easy for you, we have given you a table that has on it the single letter code, the triple letter code, the pKa of the carboxyl group and the amino group for the free amino acids. And if the R group is ionizable, it gives you the pKas. I expect you to memorize the single letter code and the triple letter code. I have some general idea that, you know, the carboxyl group's about 2, the amino group's about 9.5. Don't memorize this junk. You can look it up forever. Try to think about more important things when you're studying biochemistry.